Mm, mm. Mhm. Uh, Hello. So I waited for 10 minutes. Nobody has joined the call yet, but I'll start. This video will be recorded, so I'll upload the recording on YouTube, and so it will be available for viewing. And in case somebody joins, well, good. Otherwise, I'll just keep the call open um, after the session is done, in case somebody joins. Okay, so let's start. So the first problem that I want, this week's topic is primarily on transient behavior of cues and also characterizing two kinds of loss systems, the alarm loss system and the insight loss system, which essentially tries to predict what is the probability that an incoming person in the queue or incoming packet in the queue will not be served and will experience a drop in service. So then there are two kinds of loss systems that need to be analyzed. What I have done for this week's content is, because it was very dense and it was full of formulae, is that I myself went over the lectures and I prepared a cheat sheet because there are too many formulae to keep in mind. And hence, so this cheat sheet is right here in front of you, and I'll make it available once I'm done with what I want to cover. And so it will be available for viewing for all students. So going ahead, the first problem that I intend to solve is, let's say there is a sports facility. For example, let's say that there is a cricket stadium. No, let's take a better example. Let's say there is a big tennis court, and so actually it's like a tennis. Hello. Hi, Chandrasekhar. Can you hear me?
Oh, yes, I'm hearing.
Okay, so I guess you are in the course queuing theory in NPTEL.
Means I have interest in the king theory.
Okay, great.
I'm
So,
not registering for the examination, but I have the interest in the king theory.
okay. So, because the reason I asked is I think this is the first time I'm seeing you in the class. So I'm sorry.
Actually, I have just today only I have just seeing the course content and all this. So I have seen your mail for the class, live class.
Okay. So you just started today.
Huh.
Fine. So here's the thing. Now I have So
I
I'll
know
just,
about the Markovian queue.
you know what the Markovian queue.
Hmm.
So I'll just then start from the top. So in the previous sessions, I'm essentially covering week by week. So we have discussed probability, queuing theory, stochastic processes, and like station and the discrete time Markov chains, and then further properties of Poisson processes and continuous time Markov chains. And we have also discussed type queues where the
In any lecture, have you discussed the Geo 1?
Geo 1. So no, that's in a later week. That's in week 6, I believe. So I don't intend to go to that week
Acha, acha.
right away. So I'm just progressing
Any
week by week.
MG1?
MG1, I think no, I think those come later. So in the plan of the course, in the plan of the course, so it comes later. So initially there is a complete discussion on MM type queues, and so and then infinity queues and other topics are covered first, and then then like the people cover, and then the course instructor goes to MG1 and GO1 queues. So that comes, I think, a week later or a week or two later.
You are TA with the Selvaraju sir, or it is independent?
Yes. So it's kind of independent in the sense that I am not Professor Selvaraju's student, and I haven't had any interaction with him regarding the course contents. It's just that I am a PMRF TA, and so I'm doing this TA as a part of my PMRF fellowship, and I happen to know this topic decently well. So what I'm doing is I'm conducting weekly sessions where I summarize, where I cover, like, essentially help students solve assignment problems, not exactly the assignment problems, but solve a set of problems that make them comfortable with the topics of that week so that they will be more, they will be able to solve the assignment
Can you
problems easily.
help, for example, if we have the MM1 system ideally,
Okay.
and if I want to introduce the interjecting of customer, so how we can
Okay.
model that, you can tell me?
Could you tell me a problem? Interjecting of customer as in you want
Means
us
there
to,
is a line,
yeah.
and
Mhm.
randomly one customer is arriving. So
Yeah.
ideally he should be in the last.
Okay. So
But,
you want MM.
practically, we have seen that customer request, or might be he knows someone in line, so he requests him or her to give the space ahead of him.
Okay.
It may be in because the customer whose service is going on, definitely he will not give the space.
Mhm.
So he may request, if he is the nth customer, so he
Yeah.
may request to second customer, third customer, or the n-1th customer, or the last customer of the before joining him. But whoever
Yeah.
the last customer, he can join any arbitrary. So if I have to
Yeah.
model this interjecting of customer, how I can do? You
With
got my point?
interjections.
You got my point?
Yeah. Yeah, I understand. So,
Means
so
if
here's the thing. Yeah, I get your point. So it's a regular MM1 queue, but then customers are allowed to interject, right?
yes,
So here there are, so in textbooks, you will find a more classic situation where you have a non-preemptive queue, which is the usual MM1 queue that is and preemptive. So even this, I don't think we have covered yet. So then there are like queues and queues with vacations and stuff. So in non-preemptive, there is no preemption in the sense that it's exactly as you described. It's always last in. Sorry, it's always first in, first out, right? That is how a non-preemptive queue will work. So then this
Non-preemptive, I believe that non-preemptive or preemptive is the policy policy from the servers. Here it is
not
not a matter of server. He is requesting to customers on betting.
right. I have to think about it a bit. So here I get your point. So in preemptive queuing, actually it's yes, it's the server's decision. So then if the server determines that a
Means,
certain
whatever the
passenger,
situation I'm telling you, that is not in hand of the server. That is in hand of the customers in a queue.
yeah. So then, so what you are saying is, let's say for like, if I have to draw a Markov transition diagram, so my current state is, let's say, n, and so then the basic characteristic doesn't change, right? So n, we will go from n to n plus 1 at a arrival rate lambda, and we'll go from n to n minus 1 at an arrival rate mu. So this characteristic doesn't change. So in the sense, I think the basic characteristics, which is um, the probability that there will be n customers in the queue, and
Definitely there are the
so
n customer, but I believe that this set of the differential equation or set of the system of equation will change.
yes, so then yeah, that will change. So like expected waiting time and these kind of quantities will change. So how that will change, I'll have to think about it a bit. I don't have it at the top of my head. The essential difference will be that when we calculate usually the waiting times, let's say for a normal queue, for a new
On next Sunday, can you tell me? On next Sunday, you think you take your time. On next Sunday, can you tell me how we can do such kind of the modeling?
Okay, sure. I can check and
Not
yeah,
necessary,
because
not necessary this time only.
yeah, sure. I can think about it. The major difference that will be is that essentially when you calculate the waiting time for a customer coming in, you usually take it to be something like um, n plus 1 times the expected service time, right? Something like that, because there is one packet in service and n packets in queue, and you are coming in after that. So whatever is the expected service time, n plus 1 times that will be the waiting time of an incoming passenger or packet or whatever. Now with interjections, this will probably change to something like, so let's say the state is n. So we have to assume some kind of probability distribution, that let's say there is a uniform probability that the that this newest packet coming in, it can take up any position from 1 to n plus 1, right? Because
It may be in
uh,
last also. It may be in last also.
yeah,
If
so something
if
like
none is none of bidding
yeah,
customer allowing him,
so
he will be
then
the last.
yeah, so then if we modify this notation to be something like w n plus 1, so it's at the n plus 1th position. And so similarly, so that's actually at the n plus 1th position. And so similarly, we can write wn minus 1 till we can write it up to w1. And then so we can write some kind of w bar equal to 1 by n plus 1 summation, wi I equal to 1 to n plus 1. This should actually come out to be something simple. Like this is just intuitive idea, although I need to think about it a bit. If you take expected waiting time common, expected service time common, which actually should be 1 by mu, 1 by mu. So then this is 1 by mu times n plus 1 times, and then if you sum, because this is essentially sum of natural numbers from 1 to n plus 1. So that is n plus 1 times n plus 2 divided by 2. That's the formula. So it should roughly come out to be n plus 2 by 2 mu. I
Uh,
mean, that's
I
the,
have I have one research paper for this. So
yeah,
if you allow me, I can send to you so that in next Sunday, can you tell something about
sure,
concretely?
sure. So this was just my intuitive, I thought this probably can be a
No,
solution.
no, I
You
believe
can
that.
share in the Zoom chat. I think you are allowed to send messages. Yeah, you can share in the Zoom chat. I'll take a note of it and I'll get back to you.
And it's better you write your email so that I can note down and later on I can send that.
I prefer not to share my email. Could you share it in the chat? I'll be available next week, so you can join and we can discuss.
That's okay.
Yes, I am. As I said, I'm not the TA who is grading or dealing with any of the course administration. So I'm not required to share my email. So I'll prefer if you just share it in the Zoom chat and I can, yeah.
This is your research area, queen theory.
Uh, it is, I don't, I did take courses in queuing theory and I apply queuing theory to wireless networks. So, so, so yeah, so far I haven't faced a use case where this kind of a question actually fits. But definitely there are many other issues. So the kind of queuing
Uh,
theory that we studied.
uh, which textbook is easy to learn the queuing theory?
So I believe the course instructor has shared in the very first lecture, you'll find a good list of textbooks where a lot of detail is there. I studied different kind of a queuing theory course, which was, so I follow, I can share it in the chat, or it's actually shared in the drive link. That is shared with the course. So I have shared the book link and the solution manual too. It's called, it's a book by Burtsekas and Gallagher, professors of
So
MIT. So
it is on the site, in the course site.
it is, so it has been shared with you. So there is a drive link that has been, there is a drive link that has been shared with you, I believe, where I am uploading uh, the course materials that so whenever I take a lecture, take a class, I
So I think
take some
in a,
notes, I prepare some notes, and I also upload course materials that I use for my classes
please.
to the drive link.
Today I have only the joined the first time now, so that's I do not know exactly what.
Yeah,
So can
you
you?
can contact the NPTEL administration staff, and they will share it with you. So, but there is a drive link which I've shared, and it has a book. So I can share the link with you in the Zoom chat. It's not an issue. Uh, 1 second. So there you will find a book, like one chapter of a book to be more precise, by Botsakas and Gallagher. So I have shared it in the Zoom chat. So from that book, so I studied primarily from this book. It's a pretty concise book with detailed examples, but it is a bit focused towards communications and networks applications, but it
Okay.
does cover the theory in a concise way. You can check the drive link that I've shared. Over there, you will find this file called Queuing Data Nets, which is the book. It's freely available online from the author's official website. It's a book by some authors from MIT, and then you also have a solution manual for the problems that are there in the book. So you can check out chapter 3, and it's a pretty solid collection of problems and discussions.
Actually, I am interested for the general cues.
For that, actually, the best references are already shared by the course instructor. So you can find them even in this book. You will get there are numerous examples of general cues. Most of the problems, in fact, deal with general cues. Some problems you'll find are more specific towards applications in telecommunication networks, but you don't really need to be an expert in communications to solve these problems. There is enough context provided. So you can check out Professor Selvaraju's first lecture, where he has mentioned a list of textbooks, and I'm sure you will get it from your university library or online. So I don't remember the names off the top of my head,
I
but
think,
his lectures themselves
sir is sharing from the Klinrock and Grozen Harris.
yeah. So yeah, and his lectures are themselves have a lot of information. So I was myself preparing for today's class. I was preparing from his lectures themselves, and yeah, so I at
Sir,
least for
how
today's
I
class.
sir, how I can share that file PDF with you?
So again, you want to share a paper?
I
So
want.
isn't there a link to the paper?
I have the PDF. I have the PDF of that.
Okay, fine. You can email it to me. I'll share my email ID with you. I shared it on room set. You can
Okay.
email it to me.
Yeah, I got.
But again, like the problem that you've shared is probably might be slightly advanced for this course. But yeah, I'll see if I can.
If
Because
easily you can explain that is okay.
yeah,
Can you at present can you explain me how to how to determine the transient solution of the MM1 model?
transient solution of the MM1 model, yes. So then actually I have been like, showing this in the previous class as well. So this is MM11. So you can pretty much see the equations on the screen. So this was discussed in this week's lecture, and I myself was going over uh, the lecture. So it's actually there in great detail in this week's lectures, and I am not going over the solutions, but so these two key equations are key. So these are, as you know, these are the Kolmogorov equations, right?
Right.
So in an MM1Q at state 0, you can have two possibilities. You can have an exit to state 1, which is with rate lambda, so then that comes as a negative. That transition is minus lambda, and then you are moving into state 0 from state 1 at a rate mu. That is, when there is a service, you move from state 1 to state 0.
Right.
So then the rate of change at state 0 is, you can write it from the Kolmogorov equation, is minus lambda times P0 plus mu times V1 of t. So, and then for any other n, that is for n greater or equal to 1, you can have two possibilities of moving out, which is either you have a arrival or a service, and both of them add up, right?
No, means
So
Kolmogorov is clear. Kolmogorov is clear.
I think I got your email.
I have sent.
Yeah, yeah. So yeah, so then at higher ends you will have this kind of a behavior. Now the solution for this is actually detailed in the lecture, and I myself don't remember it in toto because it was quite involved. It required assuming it required writing some probability distributions, that is like some probability generating function and solving it. But the entire discussion is there in the lecture. I think lecture 19. It's pretty much the whole of the it's a good 6 7 minute discussion, which I don't remember off the top of my head. So, but what what essentially after all of the calculations, this is a solved problem, and so in the transient state, what you will have is some this factor of e to the power minus lambda plus mu times t times um, this a really big term which comprises sum of Bessel functions. So then now from there, if you actually, so how will you test it? So if you're, let's say, replicating the calculations, one way to really test if your calculations are correct is to take a limit st approaching infinity and then see if you reach the steady state solution. And so then, yeah, so I can. So do you want me to go over this solution
No,
approach?
you have said it is in lecture 19 of Selvaraju, sir.
Yes, it is there.
I will refer otherwise on next Sunday I will.
Yes. So it is. So I was myself going over the lectures because, like, I usually don't deal with transient state dynamics. So this was new for me as well. But I was going through, and it is pretty well explained. So each and every step is detailed, and the calculation is a bit involved, but it is there.
Sir, till now, up to what you have covered, up to what lecture? So that
I have covered. So I have covered up to week 4, which I believe is lecture 16, and all of my sessions are recorded and uploaded on my YouTube channel, which you should be getting from the NPTEL admin.
I think
And
that is in one Excel sheet. From there only I
yes,
come to know that you are taking the live lecture.
yes. So then that Excel sheet you will have the drive link. You will also have, which I shared in the chat. You will also
I have copied.
you also should have the YouTube channel and everything. So my YouTube channel will have all of the previously recorded videos in case you want to go over that and check out the discussions that happened. Yeah. So the topics that I've covered, as I said, were so the first week it was probability and basics of queuing theory, introduction to queues, and Little's law. And in the second week, I covered a bit of stochastic processes, and then moving on to discrete time Markov chains. In the third week, I covered more about Poisson
So I
random
think
variable, and
this Geo 1 come under the discrete time Markov chain only, no?
it does come. So now it does. Now it depends on the course instructor, right? How the course instructor wants to divide the course contents. You are right. It does come under discrete time Markov chains, but Geo 1 particularly as a separate topic was not covered. It comes a bit later. So when we so the way professor covers it is he first covers MM1 queues, which are exponential and exponential. So those are simpler to handle. And then he moves on to more generalized distributions. So which is MG1 and then Geo1.
So I think Selva Raju lectures are recorded one, na? Just we have to see, then we have to contact with you weekly wise.
Yes, I did. Yes. So his lectures are
Or he is
available on
also
the
presently
on
taking the lecture. He is also presently taking the lecture.
So his lectures are already available online. His lectures are already available online on YouTube. You can check NPTEL Introduction to Queuing Theory, and the same lectures are made available through the Swayam platform. But in principle, the entire course is available on YouTube. So yeah, particularly as I said, lecture 19 deals with transient solutions.
So means
And
in
GO01 queues come in lecture 27. I just have his YouTube open right now. So GO01 comes in lecture 27. So you can easily find it on YouTube. If you just Google, if you just search Introduction to Queuing Theory NPTEL, you will get his lectures on YouTube. And in lecture 27,
till now you have covered the lecture 6 up to the lecture 16 of the Selvaraju, and
yes.
next
And
time
today
you will present for the lecture 20.
Yes, exactly. Yeah.
Right. So next time when I will come with the revision of up to the lecture 20.
Yes.
Every Sunday you are taking at the 3 o'clock.
Every Sunday, 3 to 5 p.m. So next week, I think, let me check, it's week 6. So it will be probably lecture 20 to 23, I think. It's always, so you can check on the Swayam portal. So the course is divided into weeks. And so every week, so I cover the contents of every week. So this week it was lecture 17 to 19. And next week, I believe, is lectures 20 to 23. And yeah, so similarly, this will continue over the next like few weeks. Yeah, that's it.
Can you give some idea about the supplementary variable?
Supplementary variable, doesn't ring a bell. What would you explain a bit? I don't know the term exactly.
Generally, supplementary variable we use to solve this system of equation. Supplementary variable for the remaining time or for the elapsed time we take.
Okay. I have to look into it. I don't remember using this technique. So for remaining time and then solve. I need to look into it. I don't remember off the top of my head.
Means any other solution method can you tell other than the product type solution for the steady state?
Okay. So obviously one way is to solve for the transient state and then take t approaching infinity. The other method that I know of is just to draw the Markov chain and solve the balance equations and get the closed form solutions if possible. In some cases, closed form solution is not possible, so we have to go by numerical methods. That's all I know. Supplementary variables, I'm not exactly sure. So another form of solution which I wasn't aware of earlier, but I saw in this course, is when the solution for Pn is obtained by like taking the like so by taking the Z transform, which is taking something like P's like trying to solve for this.
So you are talking for the, I think, probability generating function.
Yes, so this is the probability generating function. Actually, in E, it's called the Z transform. Yeah, so this is the probability generating function. So then this solution method was used in, and especially in this set of lectures, it was used. So then, yeah, so this is, these are the methods that I'm aware of. I don't know of this supplementary variable method. I need to look it up.
And this PGF, I think in the 9th or 10th lecture of sir, it is given.
Yeah. So that has been discussed.
So There are a lot of paper of the supplementary variable. If you can help me to make it understandable in next lectures, it's good for
Yeah,
me.
I can see. So, but as you can see, this course is more intended towards beginners, and
No, it
so
is
I believe,
a part of the course also, because it is a part of the
yeah,
Cleanrock and Gross and Harris supplementary variable. Might be it come later, but that I do
yeah.
not know
So
will come. But it is a part of,
I'll
because for the MG1 we require the supplementary variable. No?
yes, we need to define like the weighting. It's just that I studied it in a more intuitive way, not by a more rigorous definition. But yes, you do need to define some supporting variables and then solve for them, and then yeah. So I can get back to you with like that, because I haven't myself gone through the reference books that are cited in this lecture. I went through some other books, but yeah. So MG1 Qs are, as I can see, it's in lectures 38 onwards. So the polar change formula. So they will come, I think, 2-3 weeks later. And for the sake of the class, I don't want to jump ahead, because even though students are not attending, they go through the recorded videos, and so I do need to cover what's on my agenda for this week. Um, for so that's a consideration that I keep in mind, and accordingly I plan. So yeah, that's there. But I'll definitely will keep a note, and I'll try next week if I can cover.
Okay, no problem. When it will come at that time, I try to understand. But
Okay.
these few things are my query about
Mhm.
the queuing problem.
Yeah.
Because basic Markovian I know, so I want to learn some advanced.
Yes. Yes. In that case, I'm not sure how this course will help you. It might be better if you, as I said, I'm not a student of mathematics, so I primarily use queuing theory for computer networks and wireless networks. So for our purposes, we are mostly fine with basic queuing theory and the models that are used. And in some cases, when we require advanced stuff, we study and apply it. But obviously, for students or for yourself and for people with a more mathematics background, operations research background, you need to go into a lot more details. So for you, I think it might be more beneficial if you can contact Professor Selvaraju himself and
Ajay, do you know
discuss that.
any other lecture available, uh, means other than NPTEL or in Coursera or in MIT, OCW or anywhere? In a complete course on the
Uh,
queuing theory?
Not really. The course I did was at NYU, and it was a condensed basic version of queuing theory, and then we moved on to different topics, which is essentially focusing on
Because
applications in networks.
wherever I have seen, they discuss only the Markovian queues.
No advanced content. Yeah, because yeah, I don't know. Then this probably is like a very niche research area. So you might not find courses, and you, as happens with research, right? Sometimes when the topics are so niche that you have to only you have to figure it out from research papers and textbooks yourself. There are no neatly designed courses. And so if yeah, so what faculty do is they try to, for advanced courses, then if they know enough about the subject matter or learning, then they themselves design a course sometimes. That's what my supervisor did. He himself designed a course and then like as a challenge and then did it. And then that helped him as well. So
No,
so that yeah,
whatever, where I can find that course, whatever your supervisor
I
has.
no. So my supervisor isn't uh, essentially a queuing theory expert. He's more of somebody who applies queuing theory to networks. So yeah, I don't know of any such really advanced queuing theory course that deals with each and every minute, like very advanced topics. My personal knowledge is limited to what's covered in this course. I haven't ventured beyond it myself. So yeah, I don't know.
Means whatever the book or lecture sir is following, do you have the solution for that also?
Uh, I don't have the assignment solutions. Uh, I I mean I try to, and and we are not allowed to provide it, but like uh, you will be provided the assignment solutions by NPTEL in due course, right? So
No,
if
no,
you check onto your
NPTEL, assignment solution NPTEL is providing week by week.
yes, yes.
But I'm asking the whatever the text or reference book sir is following. Uh,
I haven't looked at that book. There might be solution manual available. I haven't looked it up. Yeah, I haven't looked it up. I, as I said, I myself followed a different book which has its solution manual publicly made available by the authors. I haven't checked if the books that professor is referring to, Kleinrock, or if they have a solution manual or not.
so whatever you are following that you have shared in your drive link, no?
Yes, it is that. Yeah. So, yeah, that is that.
Can you check now the paper, whatever I have sent on your mail?
I think I received it. Okay. This is a master's thesis, right? This is a huge paper. Human system presented. Yeah, I can see there is a lot of Kolmogorov analysis is there, but it will take me some time to grasp this. And clearly, this is beyond the scope of the course. And if I find time, I'll definitely go through this and see if I can solve it. But this definitely is way beyond my responsibility as a TA for this course. This is this is a really hard research problem, and I'll try. If I find time, I see it's pretty detailed. So yeah, but it seems like a solved problem, right? This problem has been solved by this person. So and by using Kolmogorov equation.
Generally, we make the equation by the state of the system, how many customers we have.
Yes.
And he has formed the equation, how many customers are waiting there.
Yes.
So that is the basic
Yes. So
difference.
yeah, yeah. So then waiting times and yeah. This is a bit involved. I have to go through it. But again, like this is beyond the scope of the course. So I will see if I have time, I'll go through it. Otherwise, I'll pass.
You try.
Yeah. Okay. Anything else?
No, presently.
Okay. Thank you. Yeah, I'll cover what's there for this week. So, which is more basic stuff, which is Erlang B formula and things like that. So, um, I'll have to cover it because other students will refer to this content. So, in the remaining time that I have,
Oh,
approximately
you
an hour.
continue. You please continue.
Yeah,
You please
yeah.
continue. I'm listening. I am listening. You please continue.
Okay, sure. Then I'll continue. So, okay. So start with the first problem that I wanted to discuss. So let's say we have some kind of a sports facility with five um, with five tennis courts. Let's say, just as an example. And so five tennis courts, and obviously um, each court can accommodate one player, right? Sorry, one pair of players. So one player on either side. So one pair of players, and then in this system you have pairs coming in, pairs arrive at arrival rate lambda, which is something like 5, or let's say yeah 5 per hour, right? And average duration of a game. So, and then this process is Poisson. So they arrive as a Poisson process with arrival rate 5 per hour. And average duration of a game is, let's say, 30 minutes. And the duration is exponential. And as we know, if we flip an exponential, if the inter service time is exponential, the service rate, so the service process is Poisson. So service rate mu is nothing but 1 by 30 per minute. Or if we have to convert it to per hour, it will be 2 per hour, right? I just want to keep the units consistent. My bad. So then this is and so now I want to calculate the revenue, like the revenue rate per hour. So revenue rate per hour of the tennis court facility, because where the charge is, let's say, charge of using the facility is, let's say, something like 20 rupees per hour. So I want to calculate the revenue per hour in the steady state or in the long term. So then this falls into the ambit of something, the MM. And did I send another email? Yeah, I see another email. So okay, fine. But I'll continue. So then this is of the type MMCCQ with lambda and mu as provided earlier, and C is equal to 5, right? Because at any time there are 5 servers effectively, because there are 5 tennis courts which can accommodate the players, and then the maximum number of players that can be accommodated is 5, because so another assumption is players leave if no quote is free. That's a reasonable assumption, right? If there is no quote available, the players will not wait. And so, the ratio factor, which is R, this is nothing but lambda by mu. We can calculate it to be something like 5 by 2, right? 2.5. And we know that the probability for MMCCQ is nothing but the Erlang B formula, which is B, C, comma, R. So C here is 5, C here is 5, and R is 2.5. And so this is the answer actually. And so there is a kind of recurring way of calculating this formula. And we can kind of quickly show how to do that. And so this is a Lang B formula, which is BC comma R is R times BC minus 1 comma R divided by C plus R times BC minus 1 comma R, right? So that is, and we start with the initial value B0 comma R equal to 1. So, so then let's, how we can start. R times B 4 comma 2.5 by, let's check the formula again. C plus R times B, yeah. C, so R is 2.5. C plus R times B 4 comma 2.5. And then similarly, we can solve for B 4 comma 2.5 equal to 5, B 3 comma 2.5 by plus and so similarly B3 comma 2.5 equal to 2.5 B 2 comma 2.5 by 3 plus 2.5 B 2 comma 2.5 and then five and even and then B 1 comma 2.5 equal to 2.5 B 0 comma 2.5 by 1 plus 2.5 B 0 comma 2.5 and this quantity is equal to 1. So then this comes out to be 2.5 divided by 3.5. So that's 5 by 7. And so then we can plug it here and here and here and here, and eventually we will get some value of B 5 comma 2.5. And these are numbers that I've cooked up, so I really don't have the solution for this, but this can easily be solved. And then from here we can actually get to Erlang C formula, which is for an MMC system. And so then that comes out to be, and these are all kind of like standard results. This comes out to be C times, that's a relation between the B and the C formula. C B C comma R by C minus R plus R B C comma R. So I'm just write it down here. 5 times b 5 comma 2.5 by c minus 2.5 b 5 comma 2.5, and so you obtain c, the c formula, and then the waiting time in total will be r plus the waiting time in the queue. Sorry, the number of people served in total will be r plus the number of people in queue, and so the number of people in queue is determined by another formula, which is c times r by c minus r equal to r plus 5 times f by 5 minus 2.5, and so then r is nothing but r is 2.5, right? Yeah, 2.5. So this algebra will give us some value L, which is the average number of players being served, and then in an hour, that is per hour basis. And then if the fee is given to be 20 per hour, so the final revenue will be nothing but 20 Indian rupees, 20 times L. So this will be the answer. So this is how we solve similar problem. It's this lecture is very much dependent on formulae. That is, you need to have a cheat sheet of formulae ready with you. This is one problem. And then related to this, there is, and this is especially important in telecommunication networks, is that you want to figure out, and this especially for old days when telephone lines were analog and wired, you need to figure out as a network operator how many lines you need to lay so that your customers are served adequately. So let's say, right? So let's say you decide to, so let's say calls arrive, and you know your customer base, so you know calls arrive at a certain rate, lambda equal to something like, yeah, 2 per minute, let's say 2 calls per minute, and then the duration is, this is of course Poisson arrival process, and the duration is, let's say, the average duration is something like 5 minutes. And so this is exponential. And my bad, this is not mu, this is 1 by mu, because this time we are talking about, so the service rate is actually mu equal to 0.2 per minute, which is 1 by 5. And so what we need to figure out is how many, so you want to lay down K circuits such that the probability of call drop is less than, let's say, 5%. And you want to find out the minimum value of k such that this is true, right? And so then this needs to be solved. And so this is clearly an MMKKQ. And lambda and mu are known. R is equal to lambda by mu, which is 2 by 0.2, which is 10. And so the value that you really want is the Erlang's B formula, which is B K comma R, right? B comma 10. Now, essentially, we know that this is a decreasing function. And so we know B0 comma 10 is 1. And subsequently, you will go to, and from here you can, again, using the recurrence relations earlier, and then not repeating the calculations again. So essentially you can use recurrence relations. So from here, from B0 comma 10, you can obtain B1 comma 10. And like you can write down the formula for B1 comma 10 and plug B0 comma 10 in there, B2 comma 10, so on and so forth. And so at some point K, right, at 0 comma 10, obviously 100% of the calls are blocked.
Excuse me, sir. Yes. M comma M K K. So what the K stands here? Capacity or population?
So K is capacity, yes, and also yeah, K is capacity. So in a telecom network, like obviously if you have laid down K circuits, then at any point you can serve at most K customers.
Means it is a number of channel also.
Yes.
In communication, it is a number of channel also.
Yeah. It is also the number of channels. Yeah, so it is also the number of channels, and it is also the capacity.
And what is this B?
B is the this is the notation used in the lecture. This is Erlang's B formula. So this is nothing but, if you in an MMCC, like you probably have studied this kind of Q, right? MMCC or MM, whatever be the notation. So you have that kind of Q. So this is nothing but the blocking probability. This is nothing but PM. There's nothing but the probability that you will find this system at this
all channels are used.
All channels are used. Yes, exactly. This is
okay. You go. Please go ahead.
Yeah. So yeah, this is when all channels are used, and so essentially we know this formula, right? And we know that this expression is not something that you can solve analytically, and so you need to use this kind of recurrence relation to solve it. So that is what is detailed in the lecture as well, and also what I kind of showed in the previous problem. So similar approach needs to be taken. So you start with B0, 10 here, say, and you obtain B1, 10, you obtain 2, 10. And so progressively this value goes down, right? And so there will be a certain minimum value of K such that B K, 10 will be less than 5%. And so the only way you can find this K is through just doing the manual, or you can simply write a program for it. And you can get the smallest value of K such that your call drop probability goes below 5%, right? And yeah, and that is your answer. So as somebody who's designing a telecom network, if you want to figure out what's the minimum number of lines you can lay so that your customers are satisfied, this kind of calculation needs to be done. Is that is a direct application of Erlang's B formula. Mhm. Okay. So now we move to some. We can continue with this actually. So let's say we have an MM11Q and um, so and at a certain time, let's say we want to calculate three quantities. So this is pi I equal to, these are all steady state quantities. And I'll explain the notation in a bit. So here xn is, so we have a state in, we have the q in state n. So there are so xn is essentially number of customers seen by nth departure. And xn star is number of customers seen by the nth arrival. And we have another quantity pi I hat, which is to I, right? And xn hat is same quantity but seen by an outsider. So with this premise, I'll come back to the problem. I'll just take a short break of 2 minutes. Sorry for that.
Your voice is not coming now. Somadeep sir, your voice is not coming. I'm not able to hear you.